Today we're starting section 11.1. We're going to work on the problem on page 694. This is problem number 12. Homing. According to the Census Bureau, the distribution by ethnic background of the New York City population in a recent year was given as those numbers. The manager of a large housing complex in the city wonders whether the distribution by race of the complex's residents is consistent with the population distribution. To find out, she records data from a random sample of 800 residents. The table below displays the sample data. Are these data significantly different from the city's distribution by race? Carry out an appropriate test at the alpha equal to 0.05 level to support your answer. If you find a significant result, perform a follow-up analysis. So notice here that we're dealing with categorical data instead of quantitative data. Everything that we've done so far has been with categorical or quantitative data. When we're able to change something into proportions because we're comparing two direct proportions as in chapter 10, or we're looking at just one proportion, so you're able to ask one question. So for instance, I can say the proportion of people that are black, but I couldn't compare that to all of the other ethnicities that we see happening here. So what's changing from the last chapters to this chapter is now we're able to look at 5 different categories in categorical data and compare them all at once. Whereas before we'd have to do multiple two-proportion tests. So I'm looking at across all this board. Does this observed what happened before? Does what happened before compared to what we are seeing here? And the reason I tried to correct myself quickly about calling this the observed is because this is what we're going to be putting into our expected. We expect that the apartment is going to be just like, or the housing complex is going to be like what the regular population is. So that this is going to be our observed count, and these are going to be our expected counts when we go to put those in. Now, we want to first always start off by setting up our situation. In this case, it's good to see that organized in the way I just explained it. So we want to pull from this that we have n equal to 800, we have an alpha of 0.05, we have our races as laid out, and then we're going to break up the observed counts from the expected counts that were given to us. From there, we want to go ahead and figure out our conditions. We have the same basic 3 conditions. We still have the random sample condition, and again, that allows us to be able to infer upon the larger population and be able to use this as our estimator. Then assuming there are more than 8,000 residents in a large housing complex, again, that's going to get to our independence condition. And then finally, our large counts condition is now going to be in regards to our expected counts. We need all expected counts to be greater than or equal to 5. And if you look through your expected counts, you notice 8 is the smallest one, but it's still greater than or equal to 5. So all of these conditions have been met for us to do a chi-square test for goodness of fit. Now, there's going to be 3 different kinds of chi-square tests that we're going to use. They all come with different names. The goodness of fit test is pretty distinct from the other 2, though. So make sure chi-square test goodness of fit. I'm checking to see if our data fits what's expected to happen. Once I've established that, then I'm going to go ahead and make my hypotheses. Because remember, we wanted to see if this was statistically significant data. So our null hypothesis would be that the distribution of race in the complex is the same as the population distribution. And our alternative is that the distribution of race in the complex is not the same as the population distribution. It is possible to write these things in symbols, but I think it's much more straightforward and clear understanding if you just write it out in words. So go ahead and leave this in context of the problem. Now that we have our hypotheses laid out, we're going to go ahead and do our calculations. Now before I do that, I'm going to actually adjust this the other way so we can put this into our calculator. So what you're going to want to do is go to your calculator, and you're going to want to put your data into 2 lists. So once I have my data in my 2 lists, notice I have my observed in L1 and I have my expected in L2. Then I'm going to run the test. So stat, go over to tests. Now this is a chi-squared goodness of fit test, so you're actually going to look for where it says Goff test. If you have a newer calculator, you won't have the if you have the old calculators, you won't have the Goff test. If you have the newer ones, then you do have the goodness of fit test. So you want to make sure you're using the goodness of fit test. Observed was in L1, expected was in L2. Now it's going to ask me for my degrees of freedom. In this case, for degrees of freedom, we're not going to do n minus 1, but instead we're going to do our number of categories minus 1. So there's 5 different categories we're looking at here, so our degrees of freedom is going to be 4. And then we're going to calculate that. And we're going to copy all of this down into our answer. So using technology, I have degrees of freedom of 4. My chi-squared is given. A high chi-squared value is going to yield a low p-value. High chi-squared, low p-value. This p-value still means the same thing as it did before. So our p is in there. You see it was given in scientific notation. I wrote that out in more standard form. Definitely less than the 5% that we're looking at, so we're going to reject the null hypothesis. And then you're going to write that conclusion a lot like you had done before. There is convincing evidence that the distribution of race in the complex is not the same as the population distribution. Now remember, it says to further analyze if we got that result. So what you're going to do is you could figure this out one at a time. So when I'm doing the getting this chi-squared value, it's getting the sum of each of the chi-squared for each of those cells. And it goes over in the book how to compute that, and you can do that completely by hand. If you do that, you're going to look at each contributing factor, which comes from down here. We want to know which one is as far off. Now, this isn't the best way of reading it. You see the first one's like 0.64, this one's 0.52. We're looking to see essentially which observed is farthest off from the expected. Just looking through our raw data, I am going to guess that it's going to be in our other category. This 8 seems far lower than the expected 22 we're looking at. And again, I can keep going through here. 0.357, 0.04, that one was really close. And then I come up with all of a sudden 24.5. That one is very far off from the other ones. So that's the further analysis we want to talk about here. The largest contributor to the statistic is the other category. There were a lot more people in the other category than was expected there to be. So this is our chi-square goodness of fit test. It's our first of our chi-square tests. Our math is going to change a little bit, but you still see the similarities from what we've done before.